Gaussian processes. Let us say we have the linear model y equals to w transpose times x. Then for each w we have one line. Given a prior distribution p of w, we get a distribution of lines. Or to be more specific, for any w we get a distribution of y values calculated as x at x as y of x conditioning on w when w is sampled from p of w. And this is what we mean when we talk about a Gaussian process. We know that if p of w is Gaussian, each y is linear combination of Gaussians and is also Gaussian. In particular, we're interested in the joint distribution of y values calculated at the n input data points, x to the t equals to 1 to 3 until n. We assume a zero mean Gaussian prior to the following. P of x, which is approximated by the normal distribution with parameter 0 and alpha to the inverse times identity matrix. Now given the n by d data points x and the d by 1 weight factor, we write the y outputs as y equals to x times w, which is the n variate Gaussian with the expectations of y equals to x times the expectations of w, which is equals to 0, and covariance of y is equals to the expectations of y times y transpose, which is equals to x times the expectations of w times w transpose, then times x to the transpose. That is 1 over alpha times x, then times x to the transpose, which by the definition is equals to k. Where k is the gram matrix with elements kij equals to, by definition, is equals to k of x to the I x to the j, that is x to the I then to the transpose times x to the j, then divided by alpha. This is known as the covariance function in the literature of Gaussian processes, and the idea is the same as in the kernel functions. If we use a set of basis functions phi of x, we generalize from the dot product of the original inputs to the dot product of basis functions as by a kernel kij, which is equals to phi of x to the I, then to the transpose times phi of x to the j, then divided by alpha. The actual observed output alpha is given by the line with added noise r equals to y plus epsilon, where epsilon is approximately by the normal distribution with parameter 0 and beta to the inverse. For all n data points, we write it as alpha. R is approximated by nn, the normal distribution, with parameters 0 and cn, where such kind of cn is equals to beta to the inverse times the identity matrix plus k. To make a prediction, we consider the new data as the m plus first data point pair x prime r prime and write the joint using all m plus 1 data points. We have r n plus 1 is approximated by nn of with parameter 0 and cn plus 1, where cn plus 1 is equals to the following 2 by 2 matrix. Cn, k, k transpose, and c. With k being the n by 1 dimensional vector of k of x prime, x to the t, and t starting from 1 to 3 until n, and c equals to k of x prime plus beta to the inverse. Then to make a prediction, we calculated the p of r prime conditioning on x prime, xr, and which is Gaussian with the expectations of r prime conditioning on x prime, which is equals to k transpose times cn to the inverse times r, and the variance of r prime conditioning on x prime is equals to c minus k transpose times cn to the inverse times k. And an example is shown in figure 14.6 using linear, quadratic, and Gaussian kernels. Figure 14.6, Gaussian process regression with one standard deviation error bars. A is the linear kernel, B is the quadratic kernel, and C is the Gaussian kernel with a spread S squared equals to 0.5. Okay, So an example shown in figure 14.6 using linear quadratic and Gaussian kernels. The first two are defined as the dot product of their corresponding basis functions. The Gaussian kernel is defined directly as kg of x to the I, x to the j equals to the exponentials of minus to the minus 1 times the square of the norm of x to the I minus x to the j, then divided by s squared. The mean, which is our point estimate if we do not integrate over the full distribution, can also be written as a weighted sum of the kernel effects. That is, the expectations of r prime conditionally on x prime equals to sigma of a to the t times k of x to the t x prime, summing for all t, where a to the t is the the tth component of cn to the inverse times r. Or we can write it as a weighted sum of the outputs of the training data points where the weights are given by the kernel function. That is, the expectations of r prime conditional x prime is equals to sigma of r to the t times w to the t, where sigma for summing for all t, and where w to the t is the tth component of k to the transpose times cn to the inverse. Note that we can also calculate the variance of predictions at a point to get an idea about the uncertainty in there, and it depends on the instances that affect the prediction in there. In the case of a Gaussian kernel, only instances within a locality are effective and the prediction variance is high where there is little data in the vicinity. See figure 14.7. Kernel functions can be defined and used depending on the application, as we have previously discussed in the context of kernel machines in Chapter 13. The possibility of using kernel functions directly without needing to calculate or store the basis functions offers a great flexibility. Normally, given a training set, we first calculate the parameters, for example using equation 14.12, and then use the parameters to make predictions using equation 14.13, never needing the training set anymore. This makes sense because generally the dimensionality of the parameters, which is generally big O of d, is much lower than the size of the training set n. When we work with the basis functions, however, calculating the parameter explicitly may no longer be the case because the dimensionality of the basis functions may be very high, even infinite. In such a case, it is cheaper to use the dual representation, taking into account the effect of training instances using kernel functions as we do here. This idea is also used in the nonparametric smoothers, Chapter 8, and the kernel machines, Chapter 13. The requirement here is that Cn be invertible and hence positive definite. For this, K should be semi-definite so that after adding beta to the inverse greater than 0 to the diagonals, we get positive definiteness. We also see that the costless operation is this inversion of n by n matrix, which fortunately needs to be calculated only once during training and stored. Still, for large n, one may need an approximation. Figure 14.7 is Gaussian process regression using a Gaussian kernel with s squared equals to 1/2 and a varying number of training set. We see how variance of the prediction is larger where there is few data. When we use it for classification for a two-class problem, the output is filtered through a sigmoid, y equals to sigmoid of w transpose times x, and the distribution of y is no longer Gaussian. The derivation is similar except that the conditional p of rn plus 1 conditioning on xn plus 1 xr is not Gaussian either, and we need to approximate, for example using Laplace approximation. This is the results by Bishop in 2006 and also the results from Rasmussen and Williams in 2006. Notes: Bayesian approaches have become popular recently with advances in computational power allowing us to sample from or approximate the posterior probabilities. Truth has many cloaks. This preference of simplicity appears in many contexts as the Bayesian approach, regularization, minimal description length, or smoothing, and is at the heart of statistical inference and hence machine learning. On the other hand, the subjectivity of priors is disturbing, and there are objections to the Bayesian approach. The Gelman in 2008, for example, what is the use of a flat prior and why collect data if we already have a picked prior? Is a conjugate prior true or merely convenient? Just like with the support vector machines, in the Gaussian processes too, there are methods by which one can construct the new kernels as functions, each weighted sums of some other kernels, and these weights or kernel parameters, e.g. spreads, can be optimized by a type 2 maximum likelihood procedure, so-called because we are now optimizing not the parameters, which are the A to the transpose or W to the transpose above, but the hyperparameters on the second level.